What's up aviators, and welcome back to the Mile High Nomads. Whether you're a student pilot just starting out, a seasoned commercial pilot, or even a CFI shaping the next generation, you're in the right place. If you got a check ride coming up, this is the video you want to watch to impress your DPE. Today we're breaking down one of the most fundamental and often misunderstood concepts of flying: drag. What is it, how it affects us, and why it matters every time you step into the airplane. But before we dive in, my wife and I have a dream: to cross the United States and Atlantic Ocean in a general aviation airplane. If you're enjoying our content and you want to follow our journey, smash that like button, subscribe, and help us turn a dream into a reality. Right, back to today's mission. Grab your notepad, sharpen your pencils, and let's dive into the world of drag and level up your knowledge. When we talk about drag, we can categorize this into two main categories: induced drag and parasite drag. Parasite drag we can then categorize into three subcategories: form drag, interference drag, and skin friction drag. But first, let's talk about induced drag. In our private pilot course, we learned that induced drag is a byproduct of lift. Now, for our commercial and as CFIs, we need to be able to get a little bit deeper into this. Induced drag is a consequence of producing lift. It is a direct result of wingtip vortices created by the difference in pressure between the top and bottom of the wing. If we have our plane here and the relative wind is coming in from the front, moving over the wing, sticks close to the wing, which we call laminar airflow, and moves aft and then down into the downwash. Same for the air on the bottom of the wing. It moves aft, sticks close to the wing, and then also moves down into the downwash. Now, lift acts perpendicular to the relative wind. So if we would draw our wing and our initial lift vector perpendicular to the relative wind coming in over the wing, it will be a vertical line, and we call this lift initial. But in reality, the air over the wing is moving aft and down. So we have something that's called average relative wind. Now, with the lift acting perpendicular to the average relative wind, our actual lift vector would look something like this. And as you can see, because of that aft component of lift, the lift is not vertically up anymore. So we lose a little bit of that vertical lift. The difference between these vectors is what we call induced drag. But we are not quite there yet. Air flows from high to low pressure. This means that the high pressure air on the bottom of the wing desperately wants to go to the low pressure side on top of the wing. And by the way, if you want to know where that pressure difference comes from, please watch our video about lift. Just click on the link showing at the top. And where is the easiest place for the high pressure to join its low pressure friend? The wingtips. This results in swirling air masses known as wingtip vortices. Think of them as mini tornadoes spiraling off the tip of your wings. And the stronger these wingtip vortices, the more induced drag. And when are these vortices the strongest? When we're heavy, clean, and slow. And with clean, we mean we have our flaps up. This is usually during climb out. This is because in that setup, we need a high angle of attack to produce the same amount of lift. So with a high angle of attack, this pressure difference gets bigger, and therefore we produce bigger wingtip vortices. So why exactly do we need that high angle of attack in that specific setup? If we pull up the equation for lift, and I will try and make this easy for you. Lift is the coefficient of lift, which is our angle of attack, times half the air density, which is the current atmospheric pressure, times velocity squared, our airspeed, times the surface area of our wing. So if we're heavy, clean, and slow, that means we need to produce more lift because we're heavy, so lift goes up. We're in clean configuration, flaps are up, so the surface area of the wing is less, and we're slow, so also our velocity goes down. That means to get the same amount of lift, either both or one of the two left over needs to come up. We can't change anything about the air density, so the last one that's left is to increase our angle of attack. So now we know that wingtip vortices increase our induced drag. But how does it look like? If we draw these vortices in the drawing, it will look something like this. And what you can see here is that these vortices push down the downwash even more, which in place changes our relative wind again. Our lift is perpendicular to the relative wind, so our new lift vector will look something like this. And as you can see, the lift vector moved aft again, increasing our induced drag and decreasing our vertical lift. Now we have that covered, let's take a look at parasite drag. We can divide this into 3 different categories: form drag, interference drag, and skin friction drag. Let's start with form drag. Form drag arises from the aircraft shape disrupting the air it moves through. To simplify this, for example, you put a rock into a stream of water. Because of the shape of the rock, the water will go around the rock, gets turbulent. This will create a lower pressure right behind the rock. The same effect as with the lower pressure on top of a wing. The lower pressure will technically drag the wing towards it. This exact thing will happen with a plane flying through the air. Alright, back to our stream. What if we this time put an aerodynamical cone around the rock and drop it in the stream again? The water will flow a lot smoother around the shape than it did around the rock itself. It will stay close around the cone and join back together right after passing the object, creating less turbulent voids behind it, therefore less pressure difference and less drag. The next one in line is interference drag. Interference drag stems from the turbulent airflow at the junctions of the aircraft's parts. A few examples will be where the wings meet the fuselage, the tail junctions, and in Cessnas where the struts meet the wings and the fuselage. This air disrupts the laminar airflow around the wings and therefore create interference drag. Then last but not least, skin friction drag. The result of air's viscosity causing resistance as it flows over the aircraft surface. Air is considered viscous because it has resistance to flow. Let's get a little bit deeper into this. If we have a wing here and we would zoom in to microscopic level, we will find out that this smooth looking wing isn't actually as smooth as it looks. It is full of surface imperfections. These surface imperfections will cause a lot of friction with the first layer of air going over the wing. To draw this out, let's draw this molecule here getting stuck on the wing's imperfections. Because of the viscosity of the air, it'll disrupt the molecule above that from flowing as well. And the same for the molecules above that, until the air starts free-flowing again. This layer, up until the free flow layer, we call the boundary layer. The viscosity of the air plus skin imperfections equals skin friction drag. Now, let's move on to the last part and see how induced drag and parasite drag affect our aircraft in flight. If we draw our vertical drag axis and our horizontal velocity axis, we can start putting our drag data in. Parasite drag increases as airspeed increases. So that line will look something like this. Also, we know that induced drag is a consequence of producing lift. So it will only happen when lift is created, meaning it'll start as soon as our nose wheel leaves the runway during takeoff. So if we draw a vertical line here representing our VSO, our stalling speed in flaps out or takeoff configuration, induced drag will start something from there. As we learned before, induced drag reduces as our angle of attack gets lower. The angle of attack lowers the more we speed up. So our induced drag line will look something like this. Now we have those two lines drawn out, we can make an average line of our total drag right here. So the point where the drag is the lowest, we can call our best lift over drag ratio, or in other words, our best glide. The speed at where we have the combination of the most lift and the least amount of drag in case of an engine failure. This speed will have us cover the most amount of distance to glide to a safe location without engine power. Not to confuse with best sink, which will give us more time in the air but less distance. But those emergencies are for another video. Thank you so much for watching. Please don't forget to hit that like and subscribe button, and please let us know in the comments down below what the next lesson should be. Fly safe!